Hello everyone. In this week, we have started our journey into design and ductile detailing of reinforced concrete buildings. In the last class, we have discussed about different lateral load resisting systems such as moment resisting frame and shear wall systems. We have also looked into material specifications related to concrete and reinforcement steel. In today's class, we will define a problem for design of reinforced concrete building, which we will take it further along with our conceptual understanding. So, in this problem, we are trying to design and ductile detail a reinforced concrete moment resisting frame building. The plan and elevations are shown in figure 1. We will show you the figure, and it is to be constructed at a medium soil site which is located in seismic zone 5. Since the present code IS 13920 is based on IS 1893 2016 version, which had seismic zones 2, 3, 4 and 5, this seismic zone is of highest seismicity. Further, we are also using IS 1893 2016 for design load calculation in this case, because the present software programs allow IS 1893 2016 version. These software programs are yet to be updated for 2025 version of IS 1893. The lateral load resisting system for this building comprises of reinforced concrete special moment resisting frames SMRF. The dimensions of beams, columns, slabs and walls are shown in table 1, while the loadings apart from self weight are shown in table 2. The material properties are listed in table 3. The job is to design highlighted beam column and beam column joints along with ductile detailing for seismic resistance. Now, let us look into the figures and tables which we have mentioned over here. So, we have a building which is having 5 bays in the x direction and 2 bays in the y direction. This is x and this is y. So, we will have a total of 18 columns, out of which you can notice that the edge columns are represented as C1, the corner columns are represented as C2 and the internal columns are all represented by C3, because usually the loading is in such a way that the columns at the edge will have some moment apart from the axial compression, while the interior columns will have lesser moment. So, that is why their design is usually different. Then the building comprises of 5 stories in total. The plinth beam is at a height of 1.5 meters from the footing level, and every story is 3 meters in height. The elevation in 2 directions, that is the xz plane and yz plane, are shown over here. We have highlighted the beam column and beam column joint which are to be designed and detailed for seismic resistance. The beam between these 2 columns, this very column, and in this case you can see all the 3 beam, column and this beam column joint. These are to be designed. Okay, so now let us see that the dimensions of these columns and beams are shown over here. RB represents roof beam, FB represents floor beam and PB represents plinth beam. 1 and 2 are the 2 directions. For example, along X we have all these FB2, RB2 and PB2, while along the y direction we have PB1, FB1 and RB1. We have already talked about C1, C2 and C3. So, these dimensions are given to you. All the slabs are 125 millimeters thick. The brick wall on the periphery are 230 mm thick, while the internal brick walls are 150 mm thick. Further, there is no parapet wall at the roof level. And apart from the self weight, we also have some more dead loads. For example, floor finish load, which is 1 kilonewton per meter square at all the levels including roof level. The waterproofing load is only at the rooftop because we need to waterproof the building. So, that loading is 3 kilonewton per meter square. At other levels, waterproofing layer is not there. So, there is no waterproofing load at other levels. Live load is available on all the levels. On the roof level, due to limited accessibility, we assume that the live load is 1.5 kilonewton per meter square, and at all other levels the live load is 3 kilonewton per square meter. Let us look into the material properties. We are using M25 grade of concrete, we are using Fe500 grade of steel reinforcement. The density of reinforced concrete is assumed to be 25 kilonewton per meter cube. It is actually the unit weight rather than density, and for the brick wall it is taken as 20 kilonewton per meter cube, which includes brick, mortar and plaster. Now, we need to design these beam columns and beam column join. First of all, in order to design these members, we need to find out what are the design actions on these members. To find the design action on these members, we have done the numerical modeling of the building on StatPro. You can choose to use any of these commercial softwares. So, we are not endorsing any commercial software, but you can use either ETABS or StatPro or SAP 2000 or any other equivalent software. You can also use open source softwares as well. Okay, so in this case we have done our numerical modeling on StatPro, where we have calculated dead load and live load, and we have applied as shown in this figure. In this figure, the left panel figure shows the dead load and the right panel figure shows the live load. So, in the dead load, you can see that on the beams we have trapezoidal loading. What is the reason behind the trapezoidal loading? Because the slab loading is usually transferred in the case of two-way slab in form of trapezoid to the longer beam, and to the shorter beam it is transferred towards triangular loading. You can look into how the load from two-way slab gets distributed to the beams, and it will be very easy for you to understand. So, this trapezoidal loading comprises of the dead load coming from the slab, floor finish and the waterproofing. That is why it is the highest at the roof level, because there is no waterproofing at other levels. So, we are getting somewhere around the maximum intensity of 16.5 kilonewton per meter at different levels, and at the roof level it is 28.5 kilonewton per meter. We also have uniformly distributed load because of the masonry infill walls which are present on these floors. That loading is 9 kilonewton per meter as uniformly distributed load. There is no parapet wall, and therefore there is no uniformly distributed load over here at the roof level. This very figure which shows you the live load, it is again having this trapezoidal loading, as we have mentioned. The slab which is having the dimension of 5 meter by 4 meter, you can have a close look afterwards as well. So, this live load, the maximum intensity is 6 kilonewton per meter at the roof level and 12 kilonewton per meter at all other levels. Then the seismic load is defined as per IS 1893 part 1 2016 version. Why? Because the software is still tuned to use the seismic load directly. I could have defined the seismic load manually, but in order to save some time, I applied the seismic load which is predefined by the software based on IS 1893 part 1 2016 version. Then the load combinations are defined as per IS 456 2000, where it is given in table number 18. I have put a screenshot of the table 18 from IS 456 over here, where we get the information about various load combinations to be used. But when it comes to the modern day code, if you are using IS 1893 2025 version, then this code gives you load combinations which will not be in the IS 456. So in that case, if you are using the 2025 version of IS 1893, then you need to consider load combinations which are suitable for this. But since we have used IS 1893 2016 version, we have used the load combinations from IS 456. And after using this, we have shown the model over here. This is the building model, and these are the load combinations over here. And after doing the numerical model, we have arrived at various results. Now we are interested in knowing the design action on this beam and this column and this beam column joint, because we want to design these components only. You can design any of them, but in a real project you will have to design all of them essentially. So you need to obtain the design action on all of these. So let us look into the design action on the beam which we are intending to design in this course as a solved example. So in this case, what we observe that the beam has a maximum hogging moment of 104 kilonewton meter. Now this is based on all the load combinations. So we have considered the maximum of all the load combinations, that is the envelope maximum value. At the same time, the envelope maximum value for sagging moment is roughly 60 kilonewton meters. Then when it comes to shear force in the beam, the maximum value for which the shear for which the beam is to be designed is somewhere around 108 kilonewton. Further, we have also summarized the design action on the columns, where the design bending moment is shown over here and the design shear force is shown over here. We will look into further more details when we are designing the beams and columns. So in the next class, we will look into ductile detailing requirements related to reinforced concrete beams. We will see the design process, how we will design and do the ductile detailing of reinforced concrete beams, so that in the next class we will solve this example problem for the design of the beam which was highlighted in today's problem statement. So this problem statement will continue in parallel with the conceptual understanding. Thank you.